In the previous chapter, we looked at the various steps you will often see in reaction mechanisms. In this chapter, we're going to combine some of them to see how we can build up mechanisms from these mechanistic steps into a common class of reactions called substitution reactions. So this is the first of many types of reactions we're going to cover in this course. And you'll see again how the concepts we learned back in chapter 6 are going to kind of come together to sort of set you on this path towards seeing how reactions work. So, what is a substitution reaction? In a substitution reaction, we have some leaving group swapped out with a nucleophile. Okay, so these molecules that have leaving groups on them can undergo multiple reactions. We'll see in the next chapter, for example, we can, if we eliminate an adjacent hydrogen, we can then produce an alkene in what we call an elimination reaction. But I'm getting ahead of myself here, but in this chapter, we're just going to swap out that leaving group with a nucleophile that attacks it. So if you want to see a specific example, here we have a haloalkane, okay, or an alkyl halide, depending on what you want to call it. And here our chlorine is our leaving group, and that is swapped out for this this hydrogen sulfide nucleophile that comes in and replaces it. Okay, now you could consider this as an equilibrium and then ask yourself, which side of this equilibrium's favored? So this hopefully should be kind of ringing a bell a little bit from the chapter on acids and bases. We kind of took a similar approach here to figuring out which side of an equilibrium dominates when you consider the acids and bases on both sides. In this case, if we look at our more stable leaving group, we see which of these species is more stable, housing that negative charge. We're comparing the sulfur over here with the chlorine over here. Now, sulfur and chlorine are both on the same period, the same row of your periodic table. So it kind of comes down to which one's more electronegative. In this case, chlorine. So the chloride over here is better at housing that negative charge. Okay, and that's why this equilibrium is kind of shifted to the right. All right. So yeah, your products here are more stable than your reactants, essentially. Okay, now something to see here is that your leaving group always takes the electrons with it. So if I were to complete the arrows here, and again, this is just hypothetical. This, what I'm going to draw out, this is just one possible way this mechanism might work, and we'll get into the different ways that this mechanism can work. But let's say I put in these lone pairs so you can see what's going on here. Basically, if we have our nucleophile attacking that carbocation, okay, that's the actual electrophile here, not the chlorine. Okay, the electrophile is this partially positive carbon that's attached to that chlorine. Okay, that electronegative chlorine's pulling electron density away from that carbon, giving it a partial positive charge and making it pretty electrophilic. Anyway, if these electrons are swinging over here, now there's a hydrogen that's not shown, so we can't just form this bond and give that carbon 5 bonds. So these electrons swing over to the chlorine, and that's what gets it to leave as this chloride here. So again, I can put the lone pairs in that so you can see how everything's linked up there. Okay, so again, this is what it means to define a leaving group as something that takes its electrons with it when that bond breaks. So that's something you'll notice if you're trying to figure out, well, what's the leaving group in a situation. Okay, so with that in mind, have a look at this example down here and see if you can identify which half of this molecule is your leaving group. Okay, so you probably hopefully have figured out that these electrons, you're breaking this carbon-oxygen bond, and these electrons are going to this oxygen, and that's what's causing this ethoxide group to be your leaving group. Okay, so if you're having trouble seeing it, I'll put the lone pairs here on the oxygen so you can see exactly what's going on. There we go. There's all our lone pairs. So you can see how this carbon-oxygen bond is breaking here, and the oxygen's taking the electrons. So you're left with this carbocation, but it's this ethoxide group here that's your leaving group. Okay, so what do we need for a good leaving group, since we're going to need a good leaving group for these substitution reactions? Well, there are two criteria needed. Okay, first of all, I kind of pointed this out earlier, but you want a nucleophilic attack to occur in the course of this this reaction. So it helps to have a leaving group that's particularly electronegative. That turns the carbon it's attached to partially positive, which encourages that nucleophile to attack it. Secondly, you want something that's able to stabilize the electrons it leaves with. Okay, so for example, we've seen chloride is a great leaving group. The reason for this is the electronegativity on your chlorine, as well as the fact that it's down in period 3, so it's relatively large and squishy. It's able to house that extra electron density pretty easily. Okay, so something to keep in mind when you're looking at leaving groups. Okay, so we're going to see that alkyl halides are great candidates for these reactions because halogens, which have these leaving groups that leave as halides, as negatively charged halogen atoms, or well, ions rather, those are great molecules for these types of reactions. So let's talk about how we name our alkyl halides. Now, alkyl halides are just alkanes that have halogens as substituents. So we're going to kind of use the same rules that we saw back on the chapter on alkanes. So you identify your longest carbon chain, your longest continuous carbon chain, also known as the parent chain. Identify substituents on it, okay, whether those are alkyl groups where your chain branches off, or in this case, some halogens, okay? And then you're going to assign locants to where those substituents are located, and you put that in the name. You just have your root name from your parent chain, and you list out your substituents in alphabetical order. So here are some examples. So on the left we have 2-chloropropane, so we have a 3-carbon chain, 2, 3, that's what gives us propane, right? Remember, it's like if you just look at the carbon chain, that's an alkane, right? So hence that ane ending, and prop, of course, tells us there's 3 carbons involved. And so if we number these 1, 2, and 3, the chlorine's coming off the number 2 carbon. So it's 2-chloropropane. Just as a refresher from that chapter, there are no spaces anywhere in the name. Remember, there's a hyphen between, there are hyphens between numbers and letters, and there are commas between numbers, as you'll see in later examples. So here, our longest carbon chain has 5 carbons, so that's pentane. That's that root word there. Now, when deciding to number from the right or the left, if we start from the left, we only go 1 carbon before we start getting to substituents. If we start numbering from the right, we would have to go 1, 2, 3 carbons before we get to those substituents. So it makes sense to start numbering from the left. Okay, so here we have a methyl group and a bromine on that number 2 carbon. And of course, remember, you've got to list these in alphabetical order. So the bromine comes first. I don't know if you noticed this, but I think I mentioned this back in that chapter on alkenes, but just to jog your memory, please note that you take the root word of your halogen, that first syllable, so in this case chlor, and in this case brome from bromine, and you just add an O to it to change it into its substituent name. Okay, so chlorine becomes chloro, bromine becomes bromo. Alright, and in this example, our longest carbon chain has 7 carbons, hence that heptane ending. Out of our substituents, it looks like we start getting substituents on the left, so that's where we start numbering. We have a methyl group on the number 2 carbon, and 2 of them on the number 3 carbon, and we have a bromine on the number 5 carbon. So again, going in alphabetical order, that's 5-bromo, 2,3,3 trimethyl heptane. Now, please note that this carbon number 5 is chiral. We have a hydrogen that's not shown. We have a bromine. We have an ethyl group, and we have, just a complex branched alkyl group that's not an ethyl group. So we have 5 different groups. Okay, so you do have to say what the stereochemistry is around that chiral carbon. Okay, now since the hydrogen that's not shown is pointing away from you, this is actually relatively straightforward. Your bromine has highest priority, followed by this complex R group, followed by this ethyl group. So this kind of goes clockwise, so hence the R designation there. Quick note here, so far all we've looked at have been our IUPAC names, right? Our systematic naming. You may have noticed in lab, and just in general when reading up on alkyl halides, that some alkyl halides are referred to by their common name. Okay, so for example, you've probably come across methylene chloride as a solvent in lab, and you may see it written down, so like its name on the bottle versus its name in your lab manual might be slightly different. In one place it might be written as methylene chloride, in another as dichloromethane. Okay, so what dictates that common nomenclature? Well, it basically arises from what you treat as your substituent and what you treat as your sort of root name. Okay, so when we use our IUPAC nomenclature, we look at our carbon chain and we treat that as the main part of the molecule. So we have an alkane name here, and we end with that alkane. Okay, and we have that ane suffix because we're dealing with an alkane. We treat the halogen as a substituent, and so we use the root word there as a prefix. Okay, so we take, for example, here we have 2 carbons in our alkane, so our root word is going to be ethane. And since we have a chlorine here as our substituent, we take that root word chlor and add an O to it. So it just becomes chloroethane. Now, in the common system, we kind of flip that. You treat your halogen as the main part of your molecule, and so you end your name with that "ide" ending that you see in a lot of typical IUPAC nomenclature. Okay, so you've probably seen this back in Gen Chem, but you'll notice that for any ionic or covalent compound, that second element, that second, that nonmetal that's, listed second, it always, typically ends with that "ide" ending. Okay, as long as it's a monoatomic, right? Polyatomic ions, of course, are different, but chlorine, like if you have NaCl, you call that sodium chloride. You take that first syllable and add an "ide" suffix to it. So we're going to do the same thing here. Okay, so we take the chlorine, which is our root word here, we take the chlor, and we add "ide" to it. The carbon-containing part is now treated as the substituent. And so that means instead of being considered an alkane with something attached to it, it is considered an alkyl group. Okay, remember that's the substituent form of an alkane. So we take that root word telling us the number of carbons, in this case eth for 2 carbons, and we add a YL suffix to it. So this becomes ethyl chloride. Okay. Now notice the space between the alkyl group and that chloride ending. Okay, unlike our IUPAC nomenclature, which doesn't have any spaces. In case you're curious about the methylene chloride, because we've probably seen that in lab at this point, the carbon over here has 2 hydrogens on it, right? A CH2 group like that is called a methylene, as opposed to a methyl group, which is CH3. Okay, so it's just called methylene chloride. That carbon has 2 hydrogens and 2 chlorines attached to it. Of course, if we use the IUPAC nomenclature, we'd have to look at it from the carbon's perspective. There's only 1 carbon here, so that's a methane, and there's 2 chlorines attached to it, so it's dichloromethane. Okay, so with that in mind, take a second and practice writing out the names for these 2 molecules. All right, so let's try working these out together. So This first one, you have your longest carbon chain with 4 carbons, whether you go 1, 2, 3, 4, or 1, 2, 3, 4. So your root word here is going to be butane. Okay. Now, when we look at our substituents, we have a methyl group, and we have a bromine, and we have an iodine. Now, do we start numbering from the left or the right? If we number from either side, we only go one bond before we start getting substituents. But since we have more substituents here on the right, let's start numbering from the right. So it's 1, 2, 3, 4. So now we want to list these substituents in alphabetical order. So going off of that, we have a bromine followed by, or well, rather a bromo substituent, followed by iodo, followed by methyl. Okay, so don't forget to include locants for those. So that would be 2 bromo, 2 iodo, whoops, there's a hyphen there, and 2 methyl, or sorry, 3 methyl. That methyl group's on the number 3 carbon. So 3 methyl butane. Okay, and notice there's no space over there. It's all one word. Now, this name actually isn't complete because this number 2 carbon is a chiral carbon. Okay, so we're going to have to, sort this out in terms of priorities. This methyl group over here has the lowest priority. So if we have that pointing away from us and we were looking down on these remaining 3 groups, organizing them from lowest or highest to lowest priority, first we have this iodine, followed by this bromine, followed by this carbon, right? So this is going to go counterclockwise. So this is an S enantiomer. So S, 2 bromo, 2 iodo, 3 methyl butane. Okay. This example over here on the right is actually a lot harder than anything you would have to worry about for this chapter, and even in subsequent chapters, to be honest with you. This is kind of a silly, really silly problem. You're not going to see something this difficult on a quiz or exam, so don't panic, okay? But plus, there's a concept in here from a later chapter on alkenes. But basically here, since we've got double bonds, our parent chain has to include those double bonds, okay, in order to include it in that suffix. So our longest carbon chain containing those double bonds, both double bonds would be these 1, 2, 3, 4, 5, 6 carbons there. Okay, so our root word there is going to be, well, it would be hexane if it were by itself. With one double bond, it would be hexene. With 2 double bonds, it's actually hexadiene. That's going to be our root word here. Now, do we number from the right, from the left to the right? In both cases, we go one bond and we get to a substituent. And really, all 4 of these internal carbons have substituents. So really, the tiebreaker here is we're just going to go alphabetically. And so I'm going to number from the right because chloro comes alphabetically before methyl or propyl. So 1, 2, 3, 4, 5, 6. So this would be 2, 4 hexadiene. Okay. That tells us that there are 2 double bonds. It's a diene, okay, a dialkene. So we've got 2 of them. One is between carbons 2 and 3, and the other is between carbons 4 and 5. When you're describing where a double bond is, you just use the first number of those 2. So it's 2, 4 hexadiene. Okay. Now, of course, you've got to go on and name the other substituents, right? We've got chloro groups. We've got a methyl group over here with 1 carbon. This substituent has 1, 2, 3, so that's a propyl group. So we want to list these all in alphabetical order. So first comes our chlorines. So this is 2, 3 dichloro. I don't know if I'm going to have room to write all of this, but we'll try our best. Out of the remaining 2 groups, we have a methyl group and a propyl group. M comes before P, so this becomes 5-methyl. Oops, there's a hyphen there. Sorry, I'm squishing this all together. Okay, so 5-methyl, and our propyl group's in the number 4 position. So 4 propyl. Okay, so this actually would have all been one continuous line, so sorry about that. Okay, actually maybe I should I'll try rewriting it over here. Okay, so it's so far we've got 2, 3 dichloro, 5 methyl, 4 propyl. Oops, there's a hyphen there. 2, 4 hexadiene. Okay, you can see why this is a particularly kind of silly problem. Now, this is actually, believe it or not, not complete because we haven't talked about the stereochemistry yet. Now, if we look at this double bond here on the left, this actually doesn't have any cis-trans isomerism because you've got 2 methyl groups attached to that carbon, so it doesn't matter which way you flip them. With this double bond, on the other hand, though, the orientation of these 2 chlorines is important, and so since they are on opposite sides of this double bond, that makes this a trans isomer. Okay, so that is actually trans 2,3 dichloro 5 methyl 4 propyl 2,4 hexadiene. Once again, this is a really ridiculous name. Don't stress about something like this showing up on a quiz or exam. Okay. Okay, so let's talk a little bit more about how these things are named. So we have, when we're referring to our alkyl halide, we give Greek letters to the carbons that our halogens attach to and subsequent carbons from that. So the carbon that's directly attached to our halogen is called the alpha carbon. So you can see here we're using a lowercase Greek letter alpha to designate that. And as we count out carbons from that, we use subsequent Greek letters. So after alpha comes beta, then gamma, then delta, and so on. To be honest with you, you're probably not going to go beyond delta, so you can probably stop there. In addition to this, we can look at that alpha carbon and ask ourselves how many alkyl groups are attached to this alpha carbon. Okay, and we can give it primary, secondary, tertiary designations, kind of how we did back with carbocations not too long ago. You could have a primary, secondary, or tertiary carbocation depending on how many alkyl groups are attached to the carbon with a positive charge on it. Okay, so similarly here, when we look at our alpha carbon, okay, so not the carbon, so you've got your halogen, you've got the carbon next to it, so not that carbon, but the things attached to that carbon are what tell us whether it's primary, secondary, or tertiary. Okay. It's possible also to have go less than, have fewer alkyl groups than even primary. At that point, your carbon has 3 hydrogens attached to it, which makes it a methyl group. Okay. But again, the number of carbons that are attached to that alpha carbon tells you whether it's primary, secondary, or tertiary. Okay, so if it has only one R group attached, okay, one alkyl group, then it is a primary alkyl halide. Okay, if we have 2 groups, it's secondary, and if it's 3 groups, it's tertiary. So let's practice this. Looking at these 2 examples, all right, see if you can identify each of the halogens listed as either primary, secondary, or tertiary. Okay, and for the circled chlorines, go ahead and label the alpha, beta, gamma, and delta carbons leading away from that chlorine. Okay, so feel free to pause this video and try that out. I will point out that when it comes to designating primary, secondary, tertiary status, go off of the number of carbons specifically bonded to that alpha carbon. Okay, it's possible to have atoms other than carbon or having multiple bonds and things. That doesn't really change the designation. Okay, so here are the answers. So if you want to check your work, when we're identifying our alkyl our halogens as being part of a primary, secondary, or tertiary alkyl halide, again, look at that alpha carbon and ask yourself how many carbons are attached to it. In this case, this chlorine's alpha carbon is attached to one other carbon, and that's it. Okay, yes, it's got bonds to two chlorines. No, that doesn't affect it being a primary carbocation. Okay. Likewise here, this carbon over here, even though it has a double bond to one of the carbons, we treat that as just being, one carbon. Okay, like we count that only once. So this is actually a secondary alkyl halide because that carbon over there is attached to two other carbons. Okay. All right. Likewise, if you want to see your alpha, beta, gamma and delta carbons labeled, here you go. Okay, so notice that the carbons with your that your halogens are attached to, that's your alpha carbon, and then it goes on from there. So you've got beta, gamma, delta, and so on. You can go in multiple directions as well. You could, look at this chlorine here and say, well, that's its alpha carbon, that's its beta carbon. This is the gamma carbon for that chlorine, even though this is the delta carbon for that chlorine. Okay, so you can have competition there when this is just a designation system, right? You choose how you're, designating these alpha, beta, and gamma or delta carbons because you're using it to describe the relationship to that particular halogen. Okay. But in any case, in both these problems, we're only circling one chlorine and we're asking for the designation from there. Okay. All right. So as you've probably seen in the last couple of examples, there are lots of different molecules that you can make from alkyl halides. Alkanes are actually not particularly reactive. There's only a few reactions they'll actually undergo. Alkyl halides, on the other hand, very reactive. Those halogens are great leaving groups, and they're electronegative. They really make that molecule ready for a nucleophilic attack. So there's lots of reactions that these molecules can undergo. Okay, and we're going to get into those, but my point here is that there are a lot of applications to these types of molecules. So let's tie this in from the previous chapter. You'll recall in the previous chapter there were 4 different diagrams, 4 different mechanistic steps I showed to you. Okay, you can have a nucleophilic attack, right, where your nucleophile comes in and attacks an electrophile, forming a bond between the two. You could have the loss of a leaving group, which is literally the reverse of that process. Here you can see this leaving group leaving, and we've got our carbocation and our bromide here. But our bromide in this example is our leaving group. You can have a proton transfer, right? So that's an acid-base reaction. You have an H plus transferred from one molecule to another. Now, please note that you might not always see both molecules. In some cases, the second molecule is kind of either left out or just sort of hidden or put onto the reaction arrow just to kind of make things a little less cluttered, make things a little bit simpler. Okay. So for example, in this case here we have hydronium. You may have seen H3O plus or just H plus written on this arrow. Likewise, instead of writing water over here, we would have minus H2O on that arrow somewhere. Okay. My point here is that you might not see necessarily this transfer of protons, literally transferred, but what you would see instead is your molecule, the one that's more important, either gaining or losing an H plus. Okay, so depending on whether it's acting as an acid or a base. So in this example here, it's gaining an H plus, okay, to form this here. Right, and finally we have carbocation arrangements. So that's basically where you have either a methyl group or a hydride shift over, and that moves your carbocation from one carbon to another, which might give it a more favorable position. So for example, here we have a secondary carbocation, right? There's 2 carbons attached to that that carbon with a positive charge. By shifting this methyl group over here, we make this molecule where now your positive charge is on this tertiary site. Okay, it's a tertiary carbocation, which is much more stable. All right, so when it comes to these four mechanistic steps and substitution reactions, we always have these two steps involved in every nucleophilic substitution. There's always the loss of a leaving group, and there's always a nucleophilic attack. Okay, so both these steps have to be involved somehow in your mechanism. Okay, now how they're involved might be different, especially the order in which they happen. Okay, now a quick note here, just because these two steps are the required steps doesn't mean you can't have more steps than that. So for example, oftentimes a proton transfer will make your product more stable, or you might have a carbocation intermediate and you'll see it undergo a rearrangement to make a more stable carbocation, which will give you the product that you observe. Okay, so my point here is that there might be more steps than just your loss of your leaving group and your nucleophilic attack. Okay, so that gives us three scenarios, okay, for the order in which these steps occur. You could have a nucleophilic attack first and a loss of leaving group second. You could have a loss of leaving group first and then a nucleophilic attack second. Or you could have both these steps occur at the same time, okay, what we call a concurrent, or a concerted reaction mechanism. Okay, so let's look at those three scenarios. In the first one, we have a nucleophile attacking our carbon, our alpha carbon, and then in a later step, we have the leaving group leave. Now you'll notice that there's something wrong here. When your nucleophile attacks that carbon, it forms a bond with that carbon. Okay, so assuming that leaving group hasn't left yet, look at that alpha carbon and notice that it has 5 bonds. Okay, remember, this violates the octet rule. We don't like to draw Texas carbons, as we colloquially call them. So this is an impossible mechanistic step. Okay, so let's look at the other combinations and see if they're possible. So here we have a leaving group leaving first, followed by a nucleophilic attack on the subsequent carbocation. Okay, so here you can see you have your leaving group leave. Next you have your nucleophile attacking that carbocation, and there's the product we make. Okay, so this is possible, right? We have these two steps occurring. And basically, you have your good leaving group leave, you have this carbocation forming, and your nucleophile attacking it. Okay, and there's your product. Now, out of these two steps, one of these steps is slower than the other. It's the rate determining step, and it turns out that it's actually this first step. Okay. So we're going to go into more detail on this in a little bit, but for now, just understand that your leaving group leaving is the slow step of this mechanism, and that's what determines the rate of this. So incidentally, this is what's called an SN1 mechanism. The 1 refers to the fact that this slow step of the reaction involves just one molecule. Now, it's also possible to have both steps occur at the same time. So as your nucleophile is attacking your alpha carbon, at that same time your leaving group will leave. Okay, so even though you are forming a bond here, you're simultaneously breaking one. So your carbon stays with just 4 bonds to it. You're not changing the number of bonds to your carbon. You're not violating the octet rule. Incidentally, this is called an SN2 mechanism, the 2 referring to the fact that there are 2 molecules involved in the slow step of this reaction, which, since it's a one-step reaction, the only step of the reaction. We'll talk about this in a little bit more detail in a second. Okay, so that your 2 molecules here, of course, being your nucleophile and the original substrate. Okay, so let's look at SN2s in particular in a little bit more detail. So just to recap again, our nucleophile here is attacking our alkyl halide, or whatever our molecule with our leaving group is. And in that same concerted step, we have our leaving group leaving. Okay, so this bond is forming as this bond is breaking. Okay, and since this is just a one-step reaction, that one step is the slow step of the reaction and therefore the rate determining step. So you would notice that the rate law for this would be first order in respect to both your nucleophile and your substrate. All right, so going back to that name SN2, the N and the S stands for nucleophilic substitution. Please note the convention here is to write the N as a subscript. Okay, so we have a nucleophilic substitution, and the 2, of course, refers to the fact that this is a bimolecular slow step. Okay, so we have 2 molecules that are involved in that slow step of the reaction. Now, the other thing that we notice about SN2 reactions involves stereochemistry. Because your nucleophile comes in and attacks your substrate at the same time that your leaving group is leaving, your nucleophile can only attack from the opposite side as your leaving group. Okay, so we call this a backside attack, and it causes an inversion of stereochemistry, as you can see here. Okay, so in this example, our nucleophile is this hydrogen sulfide ion. It has to attack from the left because the bromine is occupying the space on the right. So you have the nucleophile attacking from the left, and that causes the inversion of this chiral center. Okay. Now, you could look at that from a stereochemistry standpoint or from a steric standpoint, saying like, okay, your leaving group's just occupying that space. There's no way for that nucleophile to access that alpha carbon from the same side as your leaving group. The other way to look at it is using a molecular orbital standpoint. Essentially, what's going on is the nucleophile is donating a lone pair into the antibonding orbital of that bond between the carbon, the alpha carbon, and the leaving group. Okay, so you have this antibonding orbital, and essentially the nucleophile donates electrons into this orbital, which destabilizes this bond and helps break this bond between the leaving group and the carbon. Okay, now you're going to go through a transition state then, where you have a you're simultaneously forming this bond between your nucleophile and the carbon, your alpha carbon, and simultaneously breaking that bond between the alpha carbon and your leaving group. Okay. Oh, I don't know if we've pointed this out before. When you're drawing transition states, you might often see this double dagger symbol, as it's called. This is the symbol for a transition state. All right. So, what affects the kinetics of our SN2 mechanism? Due to the necessity of a nucleophile attacking that alpha carbon, since that's what kind of drives this forward, it makes sense that the more sterically hindered that alpha carbon is, the less the reaction occurs. So basically, if you have a tertiary alkyl halide, you have these bulky alkyl groups surrounding that alpha carbon. And of course, your leaving group's blocking the other side of it. So this gives very little access to a nucleophile coming in to attack that alpha carbon. So we notice that with tertiary alkyl halides, we don't really observe an SN2 reaction. Okay, so if you're under SN2 conditions, you actually wind up not seeing a substitution if your substrate is a tertiary alkyl halide. And you'll notice that as you get less and less hindered, all the way back to a methyl group, the rate will increase. Okay, just because now your nucleophile has easier access to that alpha carbon. Okay. Now, if you want to explain this in terms of kinetics and thermodynamics, remember back to last chapter where we talked about the difference between a kinetic and a thermodynamic argument. Thermodynamic arguments look at the stability of your product. A kinetic argument looks at the size of activation energy. And this is where those sterics come in, because the more sterically hindered your alpha carbon, the more energy your nucleophile might need to access that alpha carbon. So your activation energy is higher. Okay, so if you want to compare them, here's the difference between a few of these different types of substrates. So we've got a methyl one here, primary and secondary, and you can see the activation energy increasing with each version. Okay, we don't have a tertiary one listed, but again, you can imagine that the activation energy for this would be even higher. All right, now I have to stress that this is a general rule of thumb. If you want to memorize that rule that generally, like, tertiary is, very low activity and it increases as you go towards primary, that's fine. That's probably a good way to remember it. However, my advice is don't rely too heavily on memorizing rules, but understand that concept. Why is a tertiary alkyl halide less reactive under SN2 conditions? Okay, and here's what I mean. Try this problem out. Try drawing neopentyl bromide. The IUPAC name is 1-bromo-2,2-dimethylpropane, if that helps. Ask yourself, is this a primary, secondary, tertiary alkyl halide? And then ask yourself to predict, will this undergo a substitution under SN2 conditions? Okay, so take a second and draw this molecule out. Okay, so if it helps, let's draw this together. So here we have 1-bromo-2,2-dimethylpropane. So with our propane, we have 3 carbons, okay, with a bromine coming off the number 1 carbon. And we have 2 methyl groups on that number 2 carbon. Okay, so there is our neopentyl bromide. Now, look at that alpha carbon over here. Is that a primary, secondary, or tertiary alpha carbon? Well, it's got 1 carbon coming off of it and 2 hydrogens, so that makes it technically primary, right? So if you just memorize rules, you'd probably say, oh, it's a primary alkyl halide. This is going to be very reactive. But in reality, we see that it is not. Even though there is only 1 alkyl group on that alpha carbon, it is a very, very bulky alkyl group. Okay, and as a result, we don't see a SN2 mechanism. Okay, so just general piece of advice here, like try to avoid memorizing rules. Just think about the concepts behind the rules. That's more important. All right, let's talk about SN1 mechanisms now. With SN1, again, I pointed out that the 1 comes from the fact that the slow step of this reaction is it involves just 1 molecule. So in the SN1 mechanism, there are 2 steps involved, right? In the first step, you have your leaving group leaving. In your second step, you have your nucleophile attacking that resulting carbocation. Now, if you were to guess, you'd probably look at this and say, well, that second step looks like it would happen pretty fast, right? I mean, you've got this nucleophile that's really seeking an electrophile, and we've got this unstable carbocation. I say unstable, I mean, here we're seeing a tertiary carbocation, which is relatively stable for a carbocation, but keep in mind, carbocations are charged species. They want to react with things, right? That carbon is under the octet rule. It's only got 6 electrons around it. It's got a positive charge, positive formal charge. It's going to react with a nucleophile relatively quickly, okay? Any nucleophiles that are around. So the second step here is relatively quick. It's this first step that is the rate determining step. And that is what we observe. We observe that our reaction is first order with respect to the substrate. Anyway, my point here is that since there's only 1 molecule involved in this slow step, that's where the 1 in SN1 comes from. Okay, so watch out for that. When you look at the designation for SN1 or SN2, it's talking about the slow rate determining step of that mechanism. Okay, a lot of students and myself as a student, I always used to get mixed up between the two, and you might even notice me sometimes accidentally get mixed up here, where I'll mix up SN1 and SN2 because I accidentally start thinking in terms of number of steps. Okay, so that does get sometimes a little confusing because an SN1 mechanism has 2 steps. but it's because it's got two mechanistic steps that that slow step has only one molecule involved. Okay, and vice versa, right? Your SN2 mechanism has just one concerted step. So yeah, so you do have to kind of train yourself to recognize where that one and that two in the name comes from. Okay. Okay, so if we were looking at our reaction coordinate diagram for an SN1 mechanism, you can see those two steps, right? So here's the transition state for that first step, here's a transition state for that second step, and you can see over here we have that intermediate, which is our carbocation. Okay, again, this also kind of highlights what our rate determining step is. Notice the really high activation energy for this first step to break this bond with the leaving group. Whereas the activation energy for forming the bond between our nucleophile and that carbocation is relatively small. Okay. Okay. So yeah, I think I've already kind of talked about all the different things in these slides. Okay, I already talked about that. Again, the N and the S stand for nucleophilic substitution. You're still swapping out your leaving group for your nucleophile. And of course, the 1 stands for the fact that there's only one molecule involved in the slow step of the reaction. All right, so let's compare our SN1 and SN2. Okay. Now, remember, with your SN2 mechanism, you've got two molecules involved in that slow step, and it's going to be first order with respect to both those molecules. Okay, so if you triple the concentration of your nucleophile, well, what would happen to the rate? Well, since your nucleophile it affects your rate law, because it's one of those two molecules in that SN2, in the slow step involved, tripling the concentration would triple the rate. But now look at your SN1 mechanism. Okay, is your nucleophile involved in the slow step of your reaction? And the answer is no. Remember, it's involved in that second fast step of the mechanism. So nucleophile is actually zero order in your rate law. So tripling the concentration of the nucleophile would have no effect on your rate if this were an SN1 mechanism. So this is actually a great way to experimentally determine whether your reaction is undergoing an SN1 or an SN2 mechanism. All right, now let's talk about the kinetics of SN1 mechanisms. We already talked about an SN2 where we noticed that the more hindered our substrate is, the more stuff with the more alkyl groups we have crammed around that alpha carbon, the harder it is for that nucleophile to access that alpha carbon, and we see a slower rate. Now, we notice the opposite trend for SN1 mechanisms, okay? And when we think about the mechanism, this explains it pretty, like you understand why pretty quickly, right? So think about what's happening in that slow step of your reaction, right? That at the end, your middle intermediate for this whole mechanism is a carbocation. And think back to the previous chapter and think about what makes carbocations stable. Well, remember, the more alkyl groups you have, the more electron density is pushed towards that carbocation due to hyperconjugation, right? So think back to the previous chapter where we saw how those carbon-hydrogen bonds on our alkyl groups kind of overlap with that MTP orbital on our carbocation and stabilize it a little bit. You know, so the more alkyl groups you have around that carbocation, the more we see that effect and the more stable that positive charge is when it forms. So as a result, if that carbocation is more stable and lasts a little bit longer, that gives it more time to sort of react with a nucleophile and yield product. Okay, so again, that's kind of the key thing there. You're stabilizing this carbocation, the more alkyl groups you have around it, and therefore you get a more product. All right, so here you can kind of see that effect. Again, ask yourself, is this a kinetic or a thermodynamic argument? Okay, I'll point out that your products have the same energy for both of these, so it's not thermodynamic. Notice that for your tertiary substrate, your your activation energy is much lower, okay, because again, your and also notice that your intermediate is also at a lower potential energy. Okay. Now, let's talk a little bit about stereochemistry. I pointed out with an SN2 mechanism, we see an inversion of stereochemistry due to that backside attack. You want your, you have to have your nucleophile attack from the opposite side of your leaving group. It obviously can't attack from the same side as your leaving group because your leaving group's there, right? But with an SN1 mechanism, you don't necessarily have this constraint. If you look at your carbocation, it's pretty symmetrical, right? You've got this empty p orbital. Your nucleophile can attack either side of that alpha carbon, okay? Because you've just got this trigonal planar carbocation, and it's open for attack from either side, okay? Now, that being said, you don't get a perfectly 50-50 distribution of product, okay? Instead of seeing exactly 50% of both of these things, you actually see a little bit more of the inverted product and a little bit less of the same side product. And again, like or the retention product, I should say, because what happens is your leaving group doesn't just completely disappear. There's still a little bit of Coulombic attraction here, a little bit of ionic attraction, because your carbocation obviously is a cation, it's positive. Your leaving group is negatively charged, right? It's an anion. So there's going to be a little bit of attraction here, causing your leaving group to kind of like hang around near the site where it was. So that kind of cuts down the axis of the nucleophile from that side. Okay, obviously not as bad as an SN2 mechanism where you're not going to have any chance of your nucleophile attacking from that side, but enough that it changes the percentages slightly. Okay, so yeah, you can kind of see that a little bit here. You've got a higher ratio of your inversion product here. You can see that instead of having a solid wedge for that chlorine, we have this dashed wedge for our OH group. Okay, showing that we've got more of that inversion product, right? But however, notice that it's a 35-65 ratio. It's not 0 to 100%. Okay, so that kind of should give away whether or not it's SN1 or SN2. Okay, if it was SN2, your inversion product is greatly favored, right? So that's what you're going to notice. Okay. Quick note here about our chloride leaving group. It's kind of a spectator ion, right? Notice that we don't see our sodium ion in this either, right? We just see the hydroxide becoming the alcohol group here. It's not shown here, but you basically make sodium chloride as a byproduct. Actually, to be honest with you, if this is happening in a kind of like a biphasic system, the sodium chloride would then go into the aqueous phase. Okay, or if this is happening only in an organic solvent, your sodium chloride would probably crash out as a white precipitate. Okay. All right, to summarize the difference between SN1 and SN2, we have this slide. So this slide might come in handy when you're studying, just to remind you of those similarities and differences. Okay, so remember with SN2, it's called SN2 because we have two molecules involved in the slow step of the mechanism. As you can see here, it's the only step of the mechanism, but basically our nucleophile attacks at the same time that our leaving group leaves, okay, in one concerted step. So as a result, your rate law is first order with both your substrate and your nucleophile. Due to the dependence on your nucleophile attacking your alpha carbon while that leaving group is still attached, it makes sense that the more substituents you add to that alpha carbon, the lower the rate. Okay, so tertiary carbocation or tertiary alkyl halide really doesn't undergo SN2 mechanisms. Okay, the other result of this backside attack is that you wind up with an inversion product. Your nucleophile always winds up on the opposite side as your leaving group. With SN1, of course, it's unimolecular. There's only one molecule, your substrate, involved in that slow step of the mechanism. So remember, that slow step is that first step. Okay. The second step, of course, is where that nucleophile attacks the carbocation. This is the fast or non-rate determining step. Okay, so as a result, this is just first order and substrate only. We see the reverse trend as SN2. Our tertiary alkyl halides are more reactive, which makes sense because a tertiary carbocation is more stable, lowering this potential energy and therefore lowering this activation energy. Okay. Regarding the products you make, since this goes via carbocation intermediate, and since your nucleophile can attack either side of your carbocation, you wind up having a racemic mixture. You get a mixture of both enantiomers. Okay, unlike the inversion, SN2, where you always get the enantiomer. Oh, and of course, quick note here about even though you do get close to 50-50, it's not quite perfect. Keep in mind there's a slight preference for the inversion product due to the leaving group kind of still partially blocking that access to that site. Okay, so we've kind of focused more on the nucleophilic attack and the loss of leaving group steps of our mechanism. However, I pointed out earlier that while every substitution reaction has to have those two steps, it's possible to get substitution reaction mechanisms with more steps. And those extra steps will often involve either a proton transfer or a carbocation rearrangement. Okay, and well, I guess those are your only two other options. Out of the 4 steps we learned, we've already used up 2 of them. But my point is that you will see, you do sometimes need to see those steps in your mechanism. Let me show you some scenarios of why that happens. Okay, so one of the things that causes this is that if you were looking at just the mechanism without those steps, your leaving group might not be a good leaving group, right? So here's an example of an alcohol group. An alcohol group, leaving as a hydroxide in a organic solvent is kind of less likely. Okay, so hydroxide's not a good leaving group in this situation. Okay? It might be great in like water or something, but probably not in an organic solvent like this. So we don't actually, observe. If we just had butanol, T-butanol sitting around in solution, we wouldn't just spontaneously observe it forming this carbocation. However, what speeds this up is to have an acid present. If you have an acid, you can protonate that alcohol group, and now this is really ready to leave as a very stable water molecule. So notice that water is a great leaving group. It's a nice neutral molecule as opposed to this ion over here. It's very stable, and therefore that's what kind of drives this equilibrium forward. Okay. A quick note here about SN2 substitution. Now, you might be tempted to look at that and say, well, is the leaving group as important since the nucleophile is kind of driving that mechanism forward? Okay, that nucleophilic attack is involved in that slow step. Well, having a good leaving group's never a bad thing for substitution reactions. It will still lower the activation energy for that, for that mechanism, but it lowers the transition state energy and therefore lowers the activation energy, and that will speed up your rate determining step. Okay, since there is only one step in an SN2 mechanism. Okay, so let's see this in a complete, in a real example here. So here we have tert-butanol, and again, we want this alcohol group to leave, but remember, hydroxide isn't a great leaving group on its own here. So we first react this with acid, with hydronium. Now, if you want to see the overall reaction is our tert-butanol reacts with hydrochloric acid to make tert-butyl chloride. Okay, so since you're using hydrochloric acid, there's plenty of hydronium floating around here, right? So the basically you can have this donate a proton to your terbutanol. You can see here it protonates this. You don't see, it's not shown here, but you have a water molecule just left behind here. That's the conjugate base of your hydronium. But anyway, here we have this as our new leaving group. Now this readily, leaves as a water molecule, so that's our loss of the leaving group step. And when it does, it leaves behind our carbocation, as we saw. Okay, and then of course there's plenty of chloride floating around because this is being done in hydrochloric acid. So that chloride readily attacks your carbocation and makes your product. Okay. Okay. So, so that being said, sometimes you have a good leaving group already, but you might need a proton transfer to, to try and change your nucleophile or even change your final product so that it's a more stable version of itself. Okay, so let's have a look at an example here. So in this case, if we're doing this with water as our solvent, this is an example of a solvolysis reaction, right? So essentially our solvent is the nucleophile used for this reaction. So we have lots of this nucleophile present. Okay, that helps by kind of pushing your equilibrium to the product side. Water is a weak nucleophile, right? You don't have a negative charge on this molecule, so it's not going to be particularly, yes, that oxygen's electronegative and you've got a partial negative charge there on that oxygen, but again, not the best nucleophile. So, what can we do to, to push this forward? Well, first of all, this is probably having a weak nucleophile, you're probably gonna want to use, you're probably gonna see this undergo an SN1 mechanism. Okay, again, I'm kind of getting ahead of myself here, but when we're comparing the two, we'll see that the type of nucleophile you use really drives whether the mechanism will be SN2 or SN1. But more importantly, when we get to, after our nucleophile attacks our carbocation, when we get to this step, notice that our product is charged. This is not a stable molecule, which might cause this, if this were in equilibrium, it kind of pushes it backwards a bit. So what might help move this forward is to deprotonate that alcohol group and leave behind just a neutral alcohol. Okay, so that's something to keep in mind. All right. The other thing we might notice in our SN1 mechanisms that go through a carbocation intermediate is that sometimes that carbocation rearranges to a more stable carbocation. Okay, so have a look at this molecule here. Now here our bromide is our leaving group. Okay, now this is going to undergo an SN1 mechanism. Look at your substrate, look at the resulting carbocation and ask yourself, is this likely to rearrange? Can I move either a hydride or a methyl group on a neighboring carbon and form a more stable carbocation? Okay. So I guess here let's draw a picture of this carbocation that forms. Okay, so it's basically when we have this leaving group leave, this is the resulting carbocation. Okay, now look at that carbocation. Is that primary, secondary, tertiary? Well, you've got one carbon over here, one carbon over here. This is a secondary carbocation, right? Now look at the carbons next to it. Can I move that positive charge to either of them and wind up having a better than secondary carbocation? Well, if I moved it here to the left by doing a hydride shift, this would be a primary carbocation, so that doesn't really help things. But what about here? If I could get that positive charge in this carbon, I could get a tertiary carbocation. And so that's what happens. We do a methyl shift. One of these methyl groups moves over, and we wind up getting this as our carbocation. And notice that now we have a tertiary carbocation, which is going to be much more stable. Okay, so that's something to keep in mind. Okay, like our since this is more stable and it's going to be present in a greater uh, percentage in solution, our nucleophile is more likely to attack this intermediate and make our product. So we'll actually see probably a mixture of products, but we'd probably get more of this rearrangement product. Okay? So that's something to keep in mind. All right. So when you're looking at your full mechanism and you're determining, are there extra steps here besides just my leaving group leaving and my nucleophilic attack? Okay. First, ask yourself, are proton transfers necessary? Is my leaving group a good one? Would having a proton transfer make it a better leaving group? Okay. Look at your final product. Is there a positive charge there? Would doing a proton transfer make it a more stable product? Okay. Now, we're going to look at, we're going to talk about the difference between SN1 and SN2 and what drives them forward. But one of the things to keep in mind is, is your electrophilic site a primary, secondary, or tertiary site? Remember, tertiary favors SN1 because you have a more stable carbocation. Primary favors SN2 because it's less hindered. It's easier access for that nucleophile. So something to keep in mind. If you're looking at SN1, right, look at that carbocation and then ask yourself, if this is a carbocation, is it a primary, secondary, tertiary carbocation, and will a rearrangement make it more stable? Okay, if I have a primary or secondary carbocation, can I do a rearrangement to give me a tertiary one, for example? Okay, or an allelic one. Okay. And then, of course, when you're trying to draw your product, keep in mind the difference between SN1 and SN2 products. With an SN2 mechanism, you get the inverted product pretty much exclusively. With SN1, you get a mixture of products, so sometimes it's not as important to show stereochemistry for an SN1 mechanism. All right, so with that in mind, let's try a complete problem. So here, we have this starting alcohol, and we go on to make this ether as our product. Now, note that this resulting product is achiral. Okay, so we've got two ethyl groups here. So in terms of determining whether stereochemistry is inverted or not, it's actually kind of hard to tell. Okay, so maybe don't use that alone to determine whether this was an SN1 or SN2 mechanism. Okay, but in general, see if you can, predict what reagents you'd use to make this reaction possible. So, it might help to identify what's your leaving group and identify what's your nucleophile accordingly when you look at the product. Okay, if you pause this video and have come back now, let's walk through the answer together. Okay. So first of all, you probably notice that your leaving group is this alcohol. Okay, we don't have an alcohol present on our product, and so so that's going to be our leaving group. Okay. Now another thing that probably jumps out at you is kind of the difference between these two molecules. Look at where your leaving group is and what carbon it's on, and look at where your nucleophile is added. It's actually added onto a different carbon. Okay, your leaving group left from this carbon, but your nucleophile attacked this carbon here. That should tell you something about this mechanism. Okay, there's probably a carbocation rearrangement involved here. And if there was a carbocation rearrangement, that means it went through a carbocation intermediate, which tells you that this was probably an SN1 mechanism. Okay, so we've got to start off with this leaving group leaving, and this is not a good leaving group. So what would be your first step? Well, probably making that a better leaving group. So we're going to protonate that in the presence of an acid. Okay, we have to use an acid first to protonate that OH group and get it to leave as a water molecule. And we wind up with a secondary carbocation. There's going to be a positive charge on this carbon here when that water molecule leaves. Okay? So here's the full mechanism. So here's that first step. We protonate that alcohol group, making this leaving group, which is really good, and it does. Here's our secondary carbocation. We do a hydride shift. So this hydrogen over here on this nearby, its neighboring carbon shifts over and turns this into a tertiary carbocation, which is much more stable. It is then that our nucleophile attacks that resulting carbocation. Now, what is our nucleophile? If we look at our file product, notice that we've added on a methoxy group. So our nucleophile would probably be either a methanol or a sodium methoxide. Again, I'm going to kind of summarize the differences here, but since we're undergoing an SN1 mechanism, the nucleophile isn't as important. In fact, you probably wanted to select a weaker nucleophile to encourage the SN1 mechanism, because a stronger nucleophile would encourage SN2. So we are going to use methanol here instead of sodium methoxide to provide that methoxy group that we see over here. Okay, so we have a methanol attacking that site. Okay, it's a weak nucleophile, it attacks that carbocation, and we make this resulting product. Of course, that has a positive formal charge of that oxygen, so deprotonating that makes our nice neutral product that we see here. Okay, now keep in mind that this is a flat carbocation, so that methanol can actually attack either side. So you actually get both of these enantiomers. Well, not technically an enantiomer because that's an achiral carbon, but you know what I mean. Basically, that we get, you could have that alcohol, the methanol attack either side is what I'm getting at. But rather than drawing both versions, it's enough to just say plus enantiomer, so people know that, you would have drawn both. You're showing that both do form. All right, so that was a pretty long mechanism. That involved multiple steps, multiple extra steps. In fact, the maximum number of extra steps. We had a proton transfer at the beginning, okay, to make our leaving group better. We had a carbocation rearrangement to make our carbocation more stable, and we had a proton transfer again at the end to make our product more stable. And this is in addition to our regular steps of our leaving group leaving and our nucleophile attacking. Okay, so we had, so basically we had all 7 steps, right? All 5 steps of this the maximum of 5 steps occur. Okay, so we had our proton transfer, leaving group leaving, carbocation rearrangement, a nucleophile attacking, and then another proton transfer to make our final stable product. Okay. With an SN2 mechanism, you'll sometimes see proton transfer steps. Again, it's the same reasons, right? Sometimes it helps to have a good leaving group, even with an SN2 mechanism. Sometimes you make a product that, has an extra proton on it, and you want to make a more stable product by deprotonating this, and so proton transfer is necessary towards the end of that reaction. Okay, you'll see that sometimes just in SN2 mechanisms as well as SN1, so it's always something good to keep in mind. Okay, so let's have a look here. Okay, so here I'll tell you that this is going to undergo an SN2 mechanism. Okay, we have a primary alpha carbon here. Okay, so generally this is probably not going to be good for making a carbocation, so it's probably not going to be SN1. This is going to likely be SN2. But that being said, we still have an alcohol group as our leaving group, and that's not a good leaving group. It might help to protonate it and have it leave as a water molecule. Okay, so here's the protonated version. So we do a proton transfer in the first step. Here's what that looks like. Our nucleophile comes in and, in a concerted step, has our leaving group leave. So again, this is SN2. Here's one molecule. Here's our second. That's an SN2 mechanism. All right, so that then, of course, yields the product that we see. Okay, here's another example with 2 proton transfers. So first of all, here's the initial proton transfer to turn that oxygen, into a better sort of leaving group. Leaving group here, it's kind of interesting to see it as a leaving group in quotation marks, because it's still, because it's that oxygen is connected with 2 bonds. When you break one bond, that oxygen is still attached to your original molecule. but it's still considered a leaving group because it's taking these electrons with it. Okay. But yeah, so we have an SN2 attack from our nucleophile here, and then of course our, we make this, since our nucleophile, is neutral, when we make our final product, the resulting product is positively charged, so a second proton transfer is necessary to make a neutral final product, which is more stable. Okay. So, yeah, so that just kind of like generally speeds things up. It makes our leaving group better. It makes our product more stable. That generally just kind of pushes the equilibrium towards the product side. All right, here's another example of proton transfer. You can see here that this is just in that final step. Okay, so our nucleophile attacks our leaving group is fine by itself here. So you don't need an initial proton transfer. Your nucleophile attacks and your leaving group leaves, but again, notice that your resulting product is positively charged, so that's why that proton transfer is kind of necessary as a second step. I mentioned that we're going to look at the difference between SN1 and SN2, like what favors one reaction versus another. And to be honest, we've kind of like looked at all these factors more or less already. Okay, we're just going to go into a little more detail on what it means to have these factors take effect. So when it comes to determining which mechanism is going to happen, you want to use this as kind of a checklist to go through and see, to try and determine which one you're going to observe. Are you going to observe SN1 or SN2? Okay, so the first thing to look at is your substrate. Is it primary, secondary, or tertiary at that alpha carbon? All right. Remember, we've seen that the general rule of thumb is that primary favors an SN2 and tertiary favors SN1. Okay, so generally because when you have a tertiary carbocation, that bulkiness sort of prevents your SN2, your nucleophile, attacking that alpha carbon, while at the same time it stabilizes any carbocation you would form. Okay, now again, take that, don't just simply memorize that rule, but try and think about what's driving that rule. Think about the concepts behind it, just so that if you do get some weird exception, you can kind of see why. All right. The other thing to keep in mind is your leaving group, right? So if you have a good leaving group, one that's going to leave by itself relatively easily, that might encourage an SN1 mechanism, okay, because your leaving group's leaving it. Likewise, the strength of your nucleophile also kind of determines things. A strong nucleophile kind of favors SN2, since that's what kind of drives that forward, what kind of initiates that. In the case of SN1, since a nucleophile is only involved in the fast step of the reaction, and it's therefore your mechanism, your rate law is zero order with respect to your nucleophile isn't really that important for driving that reaction. Then the last thing to consider is your solvent, and we'll get into that. Okay, so I think we've seen that carbocations get more stable as we go from primary to secondary to tertiary. And I just mentioned that in addition to this, we want to consider allelic carbocations as being particularly stable. So just to jog your memory from an earlier chapter where we discussed the difference between vinyl and allelic, remember, if something's on the carbon off a double bond, if a carbon-carbon double bond, that's the vinylic position. If it's one bond away from that, then that's the allelic position. Okay, so we've seen that allelic carbocations are stable, whereas vinylic ones are not. Okay, I wanted to introduce the term benzylic versus aryl, and the distinction here is very similar. Okay, so if you have a benzene ring, if you're on the carbon, one of the carbons off that benzene ring, it's kind of like being in the vinylic position of the benzene. Okay, so just as the allelic position makes a particularly stable carbocation, the benzylic position, which is one carbon away from your benzene ring, is also a good spot for that carbocation. When you see a benzylic position, you'll kind of see what I'm talking about. Basically, if we look at our allelic halide, again, our halogen is attached to that allelic position, right? So here's our double bond, carbon-carbon double bond. Here's our vinylic position. Here's the allelic position, and notice that our halogen's attached to that. Okay, so when this halogen leaves, this leaving group leaves, our positive charge here is going to be resonance stabilized. Okay, so basically we get this carbocation, which we can then resonance stabilize accordingly. Okay. So notice that this positive charge is delocalized between this 3-carbon system. Now, if you look at a benzylic halide here, this also has that kind of very similar to our allelic system here. Okay, that's kind of what's going on. Okay, it's the same system, right? When we break off our leaving group here, we're going to have a positive charge on this carbon. And again, we can have resonance that stabilizes that positive charge. Okay. If anything, in that benzylic position, it's actually just not limited to this, but we can actually have all of these electrons involved in that system. Okay, so here's a picture of those structures and showing that resonance stabilization. So again, this just makes that carbocation extremely stable, and we've seen, like with tertiary carbocations, a stable carbocation will probably yield product. Okay, so yeah, so something to keep in mind, that probably is going to favor an SN1 mechanism. All right. As I pointed out earlier, vinyl, when you have your leaving group in the vinyl position, that's not likely to leave. Same reason that an aryl, something at the aryl position, something that's attached directly to that benzene ring, is not going to be likely to leave. Okay, so that's, even if you've got a good leaving group here, since that resulting carbocation is not particularly stable, this isn't necessarily going to go in the forward direction. Okay, let's talk a little bit about nucleophiles, right? We want a strong nucleophile to encourage our SN2 mechanism. So what makes a nucleophile strong or weak? Okay, it helps if you have a negative charge on your nucleophile, right? So having that negative charge makes it really want to seek out a positive charge, and that means it's very nucleophilic. So we've kind of already seen this in a hydroxide versus a water molecule. Water is a weak nucleophile. A hydroxide ion is a strong nucleophile because of that negative charge. Okay. Yeah. So other things that help determine whether something's going to be nucleophilic or not. It helps to have something that's relatively stable, and it also helps to have a not sterically hindered nucleophile. Something that's particularly bulky will not make for a good nucleophile. Instead, it might act as a base. We're going to get into this distinction a little bit more in the next chapter. Because we're going to see, while in this chapter we're looking at the competition between SN1 and SN2, in the next chapter we're going to compare the competition between these substitution reactions with elimination reactions. And we'll see that nucleophiles can sometimes act as bases, and that tends to encourage the elimination reaction over the substitution. So something to watch out for. And sterics play a pretty big role in that, in making your nucleophile more like a base and less like a nucleophile. Okay, so generally speaking, though, a strong nucleophile will favor your SN2 mechanism. Okay, so here are some examples of some nucleophiles. Okay, we can see that have a look at your strong nucleophiles, look at your weak nucleophiles, and ask yourself, what sort of patterns do you notice here? Okay, you could just memorize this list of examples of strong and weak nucleophiles, but it might help to notice these patterns and ask yourself, why does this occur? Okay, so notice that typically your strong nucleophiles are all negatively charged. I think the only exceptions of neutral ones are ones with these sulfurs on them. Now, why is sulfur allowed? Remember, sulfur is relatively large. It's a large atom. It's kind of squishy, got a lot of electron density. So that's why I think it can kind of get away with that a little bit. Okay. Whereas for oxygen, you need that negative charge on the oxygen, whether as an alcohol group or an alkoxide group, to make it a strong nucleophile. If you have a neutral water molecule or alcohol, they tend to be weak nucleophiles. Okay. Fluoride is kind of interesting here. You notice that all of your halide ions are great nucleophiles. Fluoride is not, even though it's a halogen, it's negatively charged. I think this has to do with fluorine's really strong electronegativity. While electronegativity generally makes things a better nucleophile, I think the problem with fluoride is that it's a little too strong. It's a little too electronegative. In other words, it kind of holds on to other things such as protons around it, rather than attacking your carbocation or something else. So there's usually not enough of your free fluoride available to act as a nucleophile. So that's why it's listed as a weak nucleophile. So it's kind of fluoride's kind of weird in that respect. Okay, let's talk about leaving groups. We pointed out that leaving groups are great if they're pretty stable. Okay, so once it's left with its pair of electrons, if it's a stable molecule, that kind of helps. So that's why we've seen that a neutral water molecule is much more stable than a charged hydroxide ion as a leaving group. Okay. All right. You also want to consider solvent effects on that leaving group. What might stabilize it once it leaves. That's something you want to keep in mind as well. Okay. So yeah, if you look in your textbook, there's a good table like kind of summarizing some good examples of leaving groups and bad leaving groups and good ones. And again, I encourage you to look at the patterns you might observe there. Okay. Now you need a leaving group for a substitution reaction, right? Your nucleophile has to come in and it has to substitute something, so you need a leaving group. So while it might be tempting to say like, oh, like leaving is really important for SN1, it kind of affects both mechanisms. You can't have an SN2 if your leaving group doesn't leave, so that's something to keep in mind. Like a nucleophile could be a great nucleophile, but it's not going to be strong enough to make a horrible leaving group leave. Okay, so you can see here with an alkane, this is one of the reasons why alkanes are, pretty unreactive hydrocarbons. Your nucleophile is not going to be able to kick out a hydrogen and have it leave as a hydride ion. All right, so let's look at some examples of some common leaving groups we're going to see, and you're going to see why they're great leaving groups. Notice that we've got the halogens over here, okay, and we also have some sulfonates. So they're all analogs of the sulfate ion. Okay, you just have some like organic functional group, like some R group attached to that sulfur instead. Okay. In all of these cases, well, in the case of iodide, bromide, and chloride, you've got these large, squishy electronegative halogens, which are great at stabilizing that negative charge. Okay. In the case of sulfonate, it's actually resonance which helps. That negative charge is spread out between the oxygens attached to the sulfur, between all of the oxygens through resonance, and that delocalization of that negative charge makes these pretty stable. Okay. These, by the way, names tosylate, mesylate, triflate, those are all kind of common names. The tosyl part comes from the fact that this is a toluene. All right, methylbenzene is also known as toluene. Mesylate, that's a methyl group. I think that's where the me part of that comes in. Likewise, here we have trifluoromethyl, and that's where that triflate comes into the name. So in case if you ever get these all mixed up, that's what that refers to. You'll often see, I think tosylate's a very common leaving group we're going to run into over and over again. So sometimes you might not see this whole structure drawn out. You'll just see, just the name tosylate, or a TS abbreviation for a tosylate group accordingly. Okay. The last effect, of course, is the solvent, right? So your solvent is present in large quantities, right? It's dissolving everything. So you want to keep in mind how that might help your reaction. having a solvent stabilize your charged species makes a very big difference. Okay, especially in the case of our SN1 mechanism, where that carbocation lasting is kind of key for that mechanism moving forward. Okay, but that being said, even for an SN2, it's kind of important because it kind of stabilizes, the partial charges on our leaving groups and our nucleophile leaving groups. Okay, so basically for both examples, for both mechanisms, having a polar solvent is very helpful in terms of stabilizing things and bringing down that activation energy. Lowering the energy of that transition state will lower the activation energy. Okay. So yeah, another thing to keep in mind, especially with an SN2 mechanism, because your nucleophile kind of drives your mechanism forward, you want to avoid a solvent that would hinder your nucleophile. While stabilizing partial charges is great in your transition state, you don't want to bind up your nucleophile before the collision happens. Okay, so you want to be careful about that. Okay, this, by the way, is why, an example of why fluoride is not a great nucleophile. It's very easily bound up by things due to its high electronegativity. Okay, so let's have a look at some, like this reaction mechanism here. So here we have a primary alkyl halide reacting with an azide ion to make, the corresponding primary azide, and we have our bromide leaving as our leaving group. Okay, so you should, just from that substrate alone, you should be able to figure out whether this is SN1 or SN2. Right, it's SN2, right, since that's a primary alkyl halide. Okay. Now look at our solvents and notice how that affects the rate. So all of these solvents are polar, by the way. Okay. But notice that we have really low rates for these protic solvents. Okay, so these are solvents capable of hydrogen bonding. These are polar, but aprotic solvents. So they're polar, but they're not capable of hydrogen bonding. And notice the rapid increase in rate compared to our protic solvents. Okay, so that's something to keep in mind for our SN2 mechanism here. Okay, what happens with those protons? Well, if you're trying to promote an SN2 mechanism, using a polar aprotic solvent is very useful. Okay, so again, what do I mean by polar aprotic? So this is DMSO, and this is acetonitrile. Those were listed on that previous slide, and we saw they had pretty high rates. Notice that we do not have a hydrogen attached to our electronegative oxygen or nitrogen, right? Remember, those are the requirements for hydrogen bonding. You need a nitrogen, oxygen, or fluorine, but with a hydrogen covalently bonded to it to make it possible, to make hydrogen bonding possible. Here we don't have hydrogen bonding, but these are still polar molecules, right? I mean, that oxygen is electronegative compared to these carbons. So this molecule is polar in the direction of you've got a dipole moment facing that oxygen. Likewise, nitrogen's way more electronegative than this methyl group, so you kind of have a dipole moment facing that nitrogen. Okay, something to keep in mind. What your polar solvent does is it helps stabilize your nucleophile, right? We mentioned that having polar solvent molecules will stabilize the partial charges on your in your transition states and just throughout your mechanism, right? In this case, with our strong nucleophile, where we have actual formal, ionic charges here, but having those polar molecules will help kind of keep that, keep your ions ready to attack. But you don't want protons here because those kind of form a shell around that chloride ion. Okay, so that's why having an aprotic solvent, one that doesn't give off H+, is very important here. Okay, so something to keep in mind, that having a polar aprotic solvent just kind of raises the energy profile of your of your reactants. Basically, it keeps your cation and anion apart, your spectator cation here, leaving that nucleophile sort of free to attack. Okay, so that nucleophile is like less stable that way because it's not balanced out by that positive charge from your sodium ion, and that's what kind of makes it more reactive. Okay. So, oh yeah, so I guess if you're looking at your activation energy, if you're starting at a higher potential energy, the resulting activation energy is much smaller, than, if we're looking at our polar aprotic solvent, here's our starting energy. Our activation energy for our polar aprotic solvent is only this much, whereas for our protic solvent, it's this much. Okay, so that's something to keep in mind. Okay, now with SN1 though, you still want a polar solvent, but here we're going to use a protic solvent. Now, again, I mentioned a protic solvent is one that's capable of hydrogen bonding. What happens is that because it's capable of hydrogen bonding, these interactions almost border on ionic. They kind of have these hydrogens that really get around that nucleophile and surround it. Okay, this actually makes your nucleophile less reactive. It kind of shields it, or makes kind of like a shell around it that stops it from attacking your electrophilic site immediately. In the case of SN1, this is kind of important because you want to give that carbocation time to sort of develop. You need that leaving group to leave first in order for it to be an SN1 mechanism and not SN2. Okay, so that's why sort of stabilizing that nucleophile for a little bit allows that mechanism to happen. Okay, so you can see here again that protic solvent kind of lowers the energy profile instead of raising it like an aprotic solvent did. Okay, so that lowering of energy of stabilizing your intermediate stabilizing those transition states and also the intermediate will lower the activation energy for the overall process. Okay. I mentioned that this kind of explains why fluoride is such a lousy nucleophile. It gets surrounded by your protons if you're using a protic solvent, and since fluoride's so small, it's just like I said, a really tight shell around the fluoride. It kind of stabilizes it a little too well. You wind up having a fluoride that's unable to react with anything because it's already reacted with all these protons. It's kind of surrounded by these protons. Okay, so if you do want your fluoride to act as a nucleophile, it's actually very important that you use an aprotic solvent here to prevent this effect occurring. All right. So that being said, of course, you want to keep in mind these factors. You want to keep in mind what substrate you're using, the nucleophile you're using, the leaving group you're using, even the solvent, if you want to drive your reaction one way versus the other. So do you want an SN1 or SN2 mechanism? Or conversely, the question might give you the conditions and you've got to figure out whether it's an SN1 or SN2 mechanism. So look at your substrate. Look at all these factors, starting with the substrate, and go from there. So if you have a primary substrate, that tends to encourage SN2. Well, if you're doing an SN2 mechanism, you might want to think about, well, what can I do to make this more successful, to increase the rate? All right. So for an SN2 mechanism, it helps to have a good nucleophile, for example. Right. For both SN1 and SN2, you want a good leaving group regardless. So you'd probably want to fix that as well. And likewise, then for the solvent, do I want to use a protic solvent or an aprotic solvent? I know I want a polar solvent, but do I need one to be protic or aprotic? Again, remember, for an SN2 mechanism, you want an aprotic solvent, right? You don't want you don't want any protons kind of forming that shell around the nucleophile and making it less effective. Okay. So conversely, if you have a tertiary substrate, you know that that's going to prefer an SN1 mechanism, right? Because a nucleophile is less likely to attack that alpha carbon. So what do you want to do? Well, you want to again have a weak nucleophile, all right? Not so much because a strong nucleophile would then make this happen through SN2, but more because a strong nucleophile is oftentimes a strong base, and you might encourage the elimination reaction. We'll talk more about why that happens, or how that happens, rather, in the next chapter. But for now, just understand that if we want to encourage this SN1 mechanism, we want to keep a weak nucleophile. Okay. Of course, you need a good leaving group. That's kind of understood. And then when you're looking at your solvent considerations, as I mentioned, a protic solvent is going to be more useful here. Okay. These considerations especially matter if you have a secondary carbocation or a secondary alkyl halide as your substrate, because you're in between a primary and tertiary. You could really have this mechanism go either way. In fact, you might even see a mixture of products. You might see some SN1, some SN2 products. And so trying to force one versus the other, it's really important to pay attention to those other factors, your nucleophile, your leaving group, your solvent. You really want to try and control that if you want to control the mechanism that your secondary substrate is going to go through. Okay, so keep that in mind, all right? From a synthetic standpoint, these substitution reactions are really, really useful just for swapping out functional groups. Based on the nucleophile you use, you can introduce some really great functional groups through just one step. In this case, so here we've got the sodium salts of all of these things. That, by the way, will encourage SN2 mechanisms, right? Because if your sodium ion has a positive charge, the nucleophile we're adding here will all be negatively charged. So they're strong nucleophiles, right? But anyway, so those nucleophiles, though, add functional groups, right? So here, if we use sodium acetate or sodium ethanoate, to use the IUPAC name, we're turning this into an ester. We're adding this alkyl group from our substrate to that oxygen, turning this into the corresponding ester. Okay, like if we use sodium cyanide, we get a nitrile. If we use sodium thiol or sodium hydrogen sulfate, hydrogen sulfide, we get the corresponding thiol. Likewise, if we use sodium hydroxide, we get the corresponding alcohol. If we use a sodium alkoxide, we get the corresponding ether. Okay, and any sodium halide, that halogen is going to swap out whatever your leaving group is, and you get the alkyl halide. Okay, so that's something to keep in mind. So let's put this into practice. Here is the molecule that we're trying to make. We're starting from 2-chlorobutane. So draw 2-chlorobutane and ask yourself, how can I get from that to our product? Okay, so if it helps out, I'm going to draw your 2-chlorobutane here. So butane has 4 carbons, 1, 2, 3, 4. And we have our chlorine on our number 2 carbon here. Okay, so there's 2-chlorobutane. Ask yourself, how do I get from here to here? Okay, so in order to get there, first ask yourself, is this undergoing an SN1 or SN2 mechanism? What's my nucleophile? Okay, what's my leaving group? What's my nucleophile? What form do I want my nucleophile in order to encourage the mechanism I'm seeing? Do I want my nucleophile to be strong or weak? Okay. Again, I'm going to stress, if I go back to this previous slide, notice that all of these here are anions because of the sodium ion balancing them out. So they're all strong nucleophiles. If you swap out these sodium ions for hydrogens, you get the weak nucleophile versions of these things. Well, maybe not so much for hydrogen sulfide here, but most of these other things are going to be weaker nucleophiles if you have a hydrogen instead of a sodium. So for example, if you had water instead of sodium hydroxide, water is a weak nucleophile even though hydroxide is a strong nucleophile. Likewise here for your sodium alkoxide, okay? If you have, an alcohol, that's a weak nucleophile, but even though your alkoxide ion is a strong nucleophile. That's not a perfect rule of thumb. Like I said, H2S, hydrogen sulfide, is a strong nucleophile. Likewise, if we used our hydrohalic acid here, that would also be a strong nucleophile. So take that with a pinch of salt. But my point is that those are considerations you want to take into account for your, if you decide that this needs an SN1 mechanism versus an SN2 or vice versa. Okay, so if you pause this video and come back now, hopefully you've kind of figured this out. So let's walk through the answer together. Okay, so you've probably realized two things. One, you've started off, you've probably noticed that our stereochemistry, or not stereochemistry, our the position of our nucleophile hasn't really necessarily changed, right? If you look at this molecule, even though I drew it a little bit differently than the way it is here, we've got 1, 2, 3, 4. There's our butane. So our nucleophile has come in at that number 2 position. Okay, so there's no carbocation rearrangement here. Okay, so before we look at this, you're probably also looking at that site and you're saying, well, that's a secondary site, right? So that could be, we could do either SN1 or SN2 depending on whatever conditions we use. So that's something to also keep in mind. Now, looking at this product that we want to make, notice that they're very specific about the stereochemistry on it. Okay, so notice that we have, this is a chiral carbon. We have a methyl group, an ethyl group. There's a hydrogen that's not shown, and we have this alkoxy group added on, or an ethoxy group. Okay, so if we want to get this product, okay, and kind of exclusively this product, we'd probably prefer an SN2 mechanism to encourage that stereochemistry, right? If we use an SN1 mechanism, we'll probably get a mixture of products, which is not as helpful from a synthetic standpoint, right? That lowers our yield of the product we want. So we want to encourage SN2. Okay, so think about how we would have our nucleophile here. Okay, would I use ethanol or would I use sodium ethoxide? Well, sodium ethoxide would be my stronger nucleophile. Okay, so you wouldn't use ethanol as your nucleophile, you'd use sodium ethoxide. Okay, and then what about solvent? Well, again, we want to encourage our SN2 mechanism, so we'd want to use a polar aprotic solvent. Okay, so something that doesn't have hydrogen bonding. So something polar like DMSO or acetonitrile or even acetone. Okay, as as a good nucleophile for this. I think they suggest acetone because acetone is, well, I mean, DMSO is also really polar. So really, any of those would have been fine. If you had said something other than acetone like DMSO, that's fine too. But the bottom line is you need a polar aprotic solvent for this. Okay. Now, it's something to consider with bad leaving groups. You sometimes want to, you need a better leaving group, but you've got to be careful of how, an acid might affect your reaction. Okay, so basically, if we do this reaction here, we're starting off with an alcohol group, and that's going to be a poor leaving group. And we've seen before that doing this under acidic conditions will protonate that alcohol group and make it a better leaving group, right? And that's great. But another way to do this is to swap out that alcohol group for a tosylate group, which is also a good leaving group. Okay, you don't want to add an acid to this directly. Now, why is that, right? Why is why is this a scenario where you don't want that to happen? Well, the problem here, I guess, with using a having acid present when you add your nucleophile, okay, is that here your nucleophile is a cyanide, okay, and so hydrogen cyanide is kind of toxic, so you want to avoid that happening. Okay. Now, by the way, if you're wondering how do you do this, you need to basically add tosyl chloride and pyridine. The pyridine kind of takes off. It basically it kind of deprotonates this hydrogen ion, and it kind of takes away the chloride from your tosyl group, and basically the tosyl adds on to that oxygen. Okay, so you basically turn that oxygen from an OH group to an OTS group, or your tosylate group. Okay, Yeah, and so that avoids you using an acid in this reaction. Okay, so yeah, so that'll basically prevent, because if you have acid present when you add your nucleophile, you don't want to have that convert into hydrogen cyanide. Okay. Yeah. So instead we use sodium cyanide, which obviously, like, you don't want to get any of that cyanide ion onto your body in any way, but at least it's not a gas that you don't have to worry about breathing in. Okay. Oh, and of course, this is still an SN1 mechanism because of that tertiary carbocation you're going to form. So you want to use a protic solvent. So something like water is fine here. Okay, and that's it for this chapter. So let's work through these additional practice problems. Yeah, and of course, do the homework and get ready for your quiz, and let me know if you have any questions on this stuff. So let's go ahead and name these compounds here, and for the the alkyl halides, go ahead and label them as being either primary, secondary, or tertiary. Okay, so feel free to pause this. All right, and if you're back now, we can go through the answers. Okay, so there go your answers. This first example isn't an alkyl halide. This is just an alkane. So if that was kind of a trick question, I'm not sure. I think they just wanted you to name the alkane there, but it's just an alkane. We only have alkyl groups branching off of our carbon chain. So our longest carbon chain has 5 carbons. 1, 2, 3, 4, 5. No matter which way you go through it, that's, let's say I go through 1, 2, 3, 4, 5, it's still 5 carbons. I have methyl groups branching off my number 2 carbon and my number 4 carbon. It doesn't matter which way you number it, you're still going to wind up coming to that conclusion. And so it's 2,2,4,4 tetramethylpentane. Okay. With this molecule, again, looking for our longest carbon chain, you might be tempted to say, okay, 1, 2, 3, 4, 5, but keep in mind that if we start here, we've got 1, 2, 3, 4, 5, 6. So hexane is our root word. We have methyl groups on that number 2 carbon and the number 3 carbon. Okay, we have to start numbering from over here because we go one bond away and we wind up with a substituent. If we number from the opposite end, we'd have to go 1, 2, 3 carbons down before we start getting to any substituents. So we have a methyl group in the number 2 carbon, methyl group in the number 3 carbon, and a bromine on the number 3 carbon. So it's 3-bromo, because remember we want to do this in alphabetical order, and B comes before M. So 3-bromo, 2,3-dimethylhexane. For this one, our longest carbon chain is actually going from here, 1, 2, 3, 4, 5, 6, 7 carbons, right? If you start numbering from this carbon here, you would get less than 7, and that's why you have to go with this as your carbon chain. Okay? Now, at this number 4 carbon, we have this branch, but that branch is itself branched. We have substituents on that branch itself. So this is an ethyl group. So this would be 4-ethyl, right? We're at that number 4 position. We've got an ethyl group. But on that, we have, at its number 1 position, 2 chlorines. So it becomes 4,1,1-dichloroethyl heptane. Okay, heptane being that root word because you've got 7 carbons in your parent chain. Looking at our alkyl groups, looking at our halogen, sorry, the alpha carbon here has 3 carbons coming off of it, so it's tertiary. If we look at our chlorines here, and we look at this alpha carbon, we've got 2 carbons coming off of it, so it's going to be secondary with respect to each of those chlorides. All right, so let's look at this reaction. So we want to try and get an SN2 mechanism starting with this substrate. Okay, so it doesn't tell you what you're trying to make, but it's asking what kind of reaction conditions would you use to promote SN2. Okay, so think about this for a second. Okay, well, this is a secondary substrate, so that's why it's kind of open to being either SN1 or SN2. We want, what can we use to encourage an SN2 mechanism now that we're stuck with this substrate? Well, it helps to have a really strong nucleophile. Okay, so we probably want something with a negative charge, so maybe the sodium salt of something as our nucleophile. it helps to have a polar aprotic solvent. Okay, so you want to pick a polar aprotic solvent like DMSO or acetone or acetonitrile or whatever. Like any one of those polar aprotics will probably come in handy. Okay. Now, your leaving group is a good leaving group already, so you don't need to protonate this. Likewise, your nucleophile coming in is going to be anionic, so you're not going to have to deprotonate that to make it more stable. So having an acid present is probably not as important. Okay. Oh, to answer that latter question, how do you know it's going to be SN2? You could look at your product and make sure you're not getting a racemic mixture of products. You're getting just this enantiomer, assuming, of course, you're starting off, with its with the inverted. Oh, I'm sorry. This is your substrate. So you're starting off with this. You'll notice that your product has an inverted stereochemistry. So the nucleophile you see would be sticking away from you. Okay, so if you pass plain polarized light through your product, you should be able to see that it deflected only in one way. You don't get it; it's not canceled out by a racemic mixture. Okay, the other thing you could do is do some kinetic experiments and determine the rate law. If it's first order with respect to the nucleophile, then that kind of tells you it has to be SN2, because SN1 is zero order with respect to the nucleophile. All right, so that brings us to SN1. So with SN1, of course, you want a weak nucleophile. Okay, so instead of using the sodium salt of something, you want to use perhaps just that neutral molecule. Probably the protonated version of it. And then you want to make sure your solvent is polar and protic. So using water or an alcohol as your solvent would be useful. Basically, it probably helps if you, actually from a solvolysis standpoint, if you use your solvent as your nucleophile. So if you do this in an alcohol or in water, then that would probably be your nucleophile there, because those are weak nucleophiles. Okay. It might, again, you've got a good leaving group here, so you don't need to protonate that really to start off. So it's not like you need to do this necessarily in the presence of an acid. Yeah, in terms of a big mechanistic step, you're probably going to need to deprotonate your water or alcohol at the end to make your stable product. All right. And in terms of determining that this is the proposed mechanism, since you're going through a carbocation intermediate, you'll notice you'll get a racemic mixture of products, so you can shine plain polarized light on it and see that it winds up, not really getting deflected much. Or you could also do kinetic studies, and you'll notice that the nucleophile is zero order with respect to this. All right. So that being said, let's try an actual, an actual reaction problem. So here we're starting off with 2-butanol, specifically one enantiomer of it. It looks like we have the S enantiomer, so this is S2-butanol. And we're making this mixture of R and S to bromobutane. Okay, so go ahead and try and figure out what's going on. Is this SN1 or is this SN2? And how would you get these products? What reagents would you use and draw the mechanism for it? Okay, so let's walk through the answer now. You've probably figured out that this is going to be an SN1 mechanism, just from the fact that we're getting a racemic mixture of products. That should tell you that. If we only got this product, then that would have been SN2. So the fact that you've got a mixture of products tells you that an SN1 mechanism is going on. Okay, so you probably it looks like your nucleophile here is going to be HBr. Okay, you want to use bromide here as your nucleophile, but using hydrobromic acid as opposed to sodium bromide is going to be useful here. mostly because your leaving group's kind of lousy. You've got an alcohol group. Protonating it's probably going to be a good idea. So your mechanism actually starts off with that protonating step. So we start off with HBr, our hydrobromic acid, and we're going to protonate that alcohol group, turning into a great leaving group. So then our leaving group leaves, making this secondary carbocation. There aren't any rearrangements. If we move the positive charge over here, we get a primary carbocation, so that's not going to happen. And likewise, if we move here, it's still a secondary carbocation. In fact, it's the same secondary carbocation, just kind of flipped over. So there's no rearrangements here, and so your bromide nucleophile just attacks that carbocation. Since that carbocation is flat and it can attack either side, you get a mixture of products. Okay, so here we have our reactant and we have our reagent. We're doing this in the presence of ethanol. Ask yourself, what product are we going to make from this, and what's that product going to look like, and how will it get there? So it might be easier to actually just start out with this actual substitution mechanism and go from there. Okay, so maybe also ask yourself, is this going to be SN1 or SN2? Look at your substrate, look at your nucleophile, and that should probably answer that question. Okay, so start off accordingly. Okay, so hopefully you've had a chance to think about this. You paused the video and thought about this. So this is SN1, right? You've got a tertiary substrate here. And you've got a great leaving group. Bromide's a great leaving group, so that leaves, okay, in that first step of your mechanism, and you get your tertiary carbocation. Now, you want to consider, is there going to be a rearrangement? Is there anything more stable than a tertiary carbocation that's possible with this molecule? So you look at the nearby carbons, okay, so your carbocations on this carbon over here, that tertiary site, can you move it to one of the neighboring carbons and get a more stable carbocation? Well, if you moved it here or here, those would be primary sites. That's going to be less stable, so that doesn't happen. But what about if we did a hydride shift and moved the positive charge over here? Well, notice that this position is allelic to this double bond. So you actually wind up getting a carbocation rearrangement for a more stable carbocation, this allelic carbocation. Okay, so here's what that looks like. Okay, so you have your leaving group leave. Here's the resulting tertiary carbocation. Here's the hydride shift that then yields this carbocation, right? So keep in mind though, this is an allelic carbocation. Due to the resonance, we actually wind up having two possible pathways. Okay, so here's the original carbocation, here's what its resonance structure looks like, and notice that here we've got a positive charge on this carbon here. Okay, now you might be tempted to say that this is a primary site and this is a secondary site, so why does this happen? And you might even see, there are factors that lead into this, right? We do want to consider the stability of this carbocation, but there are thermodynamic reasons as well for why we see the products we do. Again, I'll get into that at the end. But the bottom line is, let's have our nucleophile attack each of those intermediates. So when our alcohol here attacks this, our ethanol here attacks this nucleophile, we get this corresponding protonated ethoxy group. And of course, that's got a positive formal charge in that oxygen. So we want to deprotonate that to yield our final product. Okay, now again, this is SN1, and that alcohol can attack either side of this, so we're going to get both versions of this molecule. Okay, that's a chiral carbon, that gets formed, and so you're going to get the enantiomer as well. Now let's look at this molecule here. So again, your alcohol will attack that carbocation. That's not a chiral carbon, by the way. There's going to be two hydrogens here. So even though it can attack either side, it doesn't really matter. You're going to get the same molecule regardless. But once again, this oxygen's protonated. You want to deprotonate it. So another ethanol comes along, deprotonates it, and that gives you this stable molecule. Okay. Now, that being said, I pointed out that there are thermodynamic considerations to think about which product's more favorable. Because you might say, from a kinetic standpoint, okay, that carbocation is secondary, and that one's primary. But in both cases, they're resonance stabilized. That positive charge is delocalized to a certain extent. So this is not like a straight up regular primary carbocation. Okay. You're still going to have a relatively low energy transition state for this. And that being said, out of our two products, this alkene on the right might be a little bit more stable. When we get into the chapter on alkenes, we'll see that the more substitutions we have on our alkene, the more stable it is. So this di-substituted alkene is a little bit more stable than this mono-substituted alkene. Okay, and so that kind of also might affect your percentage of products. That being said, you probably have a healthy percentage of both products, so it's useful to draw both of these products. Okay, it's not like you're going to have only one versus the other. All right. So I think that is it. And yeah, so please do the homework. Let me know if you have any questions on this stuff, and yeah, good luck on the quiz.